I'm going to be talking about Danish males' mortality for reasons that I'll explain when we get a few slides in. Before I go on, I want to acknowledge the collaborators on this project. So I've got David Blake and Kevin Dowd, I've been working with them for quite a number of years on various, perhaps often more financial risk-related projects, and then over the last 10 or 15 years, we started to move into looking at mortality, as particularly where mortality risk and randomness in mortality actually had an impact on financial risks within pension funds. And so that was how I came into this general area. And then a few years ago, we teamed up with Milena Kallestrup-Lam in Aarhus and Karsten Rosenkjold, who's her PhD student, and the reason for that was that they have access to a fantastically good data set that they have in Denmark, which I'll describe in the coming slides. But before I go on to that, this slide here is just telling you a bit about a bigger research project, which is in a sense just starting off, but today's talk is very much feeding into this particular bigger research program. It's a program of research that's funded by the Institute and Faculty of Actuaries through its Actuarial Research Centre, which is effectively the body which will oversee the commissioned or funded research that comes through the profession, both larger projects like this one and also smaller funded research projects, and of those might be shorter term and things like PhD scholarships. But this particular research program, it's looking at a number of strands. So one of them is looking at new mortality models for forecasting mortality in particular, because that's what the actuaries are interested in, what's going to happen in the future, rather than getting a overly detailed understanding of the past. And then those models will then be applied in a way that will think about how do pension funds and life insurance companies manage those risks, looking at underlying drivers of mortality, and then lastly modelling morbidity risk for critical illness insurance. And this is where there's a particular connection with Erin Gould in your department here, so she will be contributing to that particular project with, and in particular working with a colleague of mine, George Streff-Taris. So as I say, today's talk, the Danish mortality and the models that underpin what I'm talking about, they're feeding into the first of these projects, but the Danish work will be developed further as part of this bigger research program. So the outline for this talk is that I'll give a bit of introduction and motivation for multi-population modelling. So we're here looking at a model, a stochastic model, where we're not looking at a single population, but we're subdividing, in this case, the Danish population. So it's thinking about multi-population modelling as well as the socio-economic side of things within Denmark. I'll then talk about constructing the new data set and what the challenges were in doing that, and then thinking about modelling that Danish subpopulation mortality. And then one of the key questions that we were looking at as part of this analysis, so there's some interesting things to be said in terms of the historical socio-economic dynamics within the population. But for actuarial purposes, one of the things that we're interested in looking at is what are the correlations between different subpopulations of the Danish males. And then finally applications. So the stochastic mortality modelling that I'm looking at, so this is a sort of stochastic mortality 101 in one slide. So the idea here is that you start off with little n lives. You've got a probability little p of survival over whatever time period it is that you're interested in, capital N survivors. So that's the random variable. And if you have the unsystematic mortality risk, that's really saying that the number of survivors, capital N, that has a binomial distribution, but that's provided you know what the value is for that little p, that probability of survival. So if you know this value or the value for p, then the risk that you have is diversifiable, and that's from the point of view of an insurance company, for example. That's why insurance works. That a lot of risk is diversifiable because you have lots of individuals rather than just one or two. So that the larger the portfolio of lives that you're looking at, if you're an insurer, the more you can diversify that risk. And in statistical terms, it's just saying that capital N over little n, that tends to p as n goes to infinity. But all of that is given that you know what p is. What the actuaries are interested in, and many other people, are what I call systematic mortality risk. And the key point here is that this survival probability p, as I've written it on this slide, this is actually an uncertain quantity. We don't know exactly what that value is. So for example, simply by the fact that you have a finite sample from history, that therefore there is some uncertainty in what the value of p is, based on that sort of estimation risk. But more importantly, for many applications, is that the further you look into the future, the more uncertain the survival probability or mortality rates, the more uncertain these are. Because historically we have seen mortality improving, but over different periods of time the improvement rates have changed, and also at different ages, different patterns of improvement at different ages. So there is certainly uncertainty in where mortality rates are going to go in future years. And so this survival probability p that I'm looking at on this slide, that there is a certain amount, some uncertainty in that. More uncertainty the more you look into the future, and it's that risk that I'm concerned with rather than the diversifiable risk that we have up above. So for longevity risk, in particular, the risk from, say, a pension fund's point of view or an insurer's point of view, that an insurer that sells annuities, their concern is that in aggregate, people are going to live longer than you anticipate. So the key points, as I've highlighted in colour, are the in aggregate. So it doesn't matter if some people unfortunately die early but other people live longer. It's what happens on average. That's what the insurance company is concerned with. So that's the in aggregate part. And then than anticipated, and I put anticipated rather than the statistically more precise expected. But the key point here is that by talking about anticipated mortality, I'm building in some expectations about future mortality improvements within that statement. So we can build in mortality improvements, but it's if people live longer than that particular forecast, then that's the risk to the insurer, because if they live longer, then financially the insurer is going to have to pay out more, or the pension fund has to pay out more money than they had put aside today for that future contingency. Now, moving on from that basic bit of motivation, and now thinking about multi-population mortality. So this is building on 2 decades or more of research, mostly on single population mortality models. When you look at single populations, whatever the data set is that you're looking at, but typically national populations, there are lots of data sets that you can work with, and you can try out your favorite model on a number of different national data sets. But when it comes to multiple populations, it becomes much more challenging simply on the data side, unless all you're interested in is to look at 2 or 3 countries. But often, and in particular, if you're looking at sort of pension funding problems or insurance companies, then they're interested in what's happening to my particular subpopulation relative to the national population. So what we're often trying to do is to think, well, can we find a good data set that is representative of a particular type of individual within the bigger population? And so but that's where the challenges lie, because often these sorts of data sets simply don't exist for a variety of reasons. So just simply getting a good data set which is a subpopulation rather than just another national population, that's a bit of a challenge, and sometimes these data sets exist but people won't give them to you for commercial reasons. So getting those data sets is tricky. And then it's also about how good quality is that data and what sort of depth. So we're looking at how, if you do get a data set, a subpopulation, how many lives are covered? Is it very small compared to the national population? But also what range of ages and how many years, how many calendar years do you have within that data set? So the national population, you may have 50 or more years worth of data, but good quality insurance data set or pension fund, you're lucky if you say get 10 years or 15 years at most. So again, that there are particular challenges there to be overcome when it comes to modelling. And then when we think about model complexity, so putting the data to one side, so just simply assuming that you do have a data set to work with single population models, there's been a tendency in particularly in the actuarial literature, to go for more and more complex models which better and better explain what we have observed in the historical mortality over the last 30 or 40 years. But that complexity also it doesn't necessarily bring with it better forecasts, and certainly not more forecasts that are maybe less robust rather than more robust. But when you then move to two populations, all of that complexity becomes even more challenging because you're having to think about, in stochastic terms, you have to think about what are all the correlations between all of the different variables. And so if you have, say, 3 period effects and a cohort effect in your model, all being modelled as stochastic processes, then you have to think about the short and the longer term correlations for all of those. So, and then of course if you go from instead of 2 populations to multi-population, which is what I'm doing here, it becomes yet more complex, and you have even more parameters that you have to estimate. And of course, with limited amounts of historical data, the reliability of the model then becomes very questionable. So really, if you're going down the road of looking at multi-population models, what you're wanting to do therefore is to take a few steps back in terms of the complexity and go for, as a starting point, single population models that are relatively simple with maybe just 1 or 2 random period effects, and also with relatively simple dependencies between the populations. So that's the starting point. Try fitting that model, and then if it fits well and explains things reasonably well, that's good, but only add complexity if after this first round of modelling, if you really have a poor fit to the data that you've got. So now moving on now to the case study, the Danish mortality and the model that we've developed to go with that. So the key point is that subpopulations in terms of their dynamics are going to differ from the national population. And of course the reasons for that are well known. So there will be socio-economic factors which push mortality rates up or down relative to the national population. But then there are lots of other factors which are also factors that influence mortality rates, such as smoking and many other things. So there's lots of factors which can influence mortality, but I'll be focusing on the socio-economic ones. In Denmark, they have a fantastically good system where people don't object to having identity cards and things like that. So they have a national register database which contains all sorts of information about each individual in the population. So everybody has a single number, a personal identifier, and you have the basic information such as date of birth, but it also includes things like how much, what level of education did you get, when did you last go to the doctor, and what drugs did the doctor prescribe, where do you live, who are you married to, but also for our purposes it includes useful information about income and wealth. So the data set runs from 1981, and for us it goes up in terms of accessibility, it goes up to 2012. And we're going to use that to subdivide the population using the covariates that are available on that database. And then, obviously, we don't just want to think, well, what are the conclusions about the Danish population? But really, what we want to do ultimately is to think about what can we learn about from the Danish data, where we have good data. What can we perhaps take away that might be useful information about modelling other populations. So for the Danish population, we've got wealth and income, and I'm going to use both of those to construct a single index for each individual. And the key reason for using wealth and income is the following. So, because in the whole process of this research, which took many years to finally get to a good result, was that if you were to look at income on its own, then yes, high income does suggest that you are affluent, and it definitely predicts low mortality. On the other hand, people who are recorded as having low income, these are which might suggest that they are not affluent, but the reality is that is not actually a very good predictor of high mortality, and that's particularly in retirement. And the reason for that is that somebody might have a low income, so this is what your taxable income, but it might be that you've got a very considerable savings and you draw an income from that, and of course that's not reflected in the income that is available on that particular database. Similarly, in terms of wealth on its own as a covariate, a high level of wealth is, again, a good predictor of low mortality, but low wealth, for the similar reasons, is not a good predictor of high mortality. And it's a similar but a different reason, that somebody might not have substantial personal assets, but they may have a very substantial pension that they're drawing, so they would have a high income. So empirically, we didn't do any genuine optimization here. We just went for a rather pragmatic solution, that was to combine wealth and income in a simple linear fashion. This is what we refer to as affluence, the affluence index for each individual. And as a pragmatic solution, we took wealth plus 15 times income. We tried 10 and 20, and all of those gave rather similar results in terms of the subdivision of the population and the consequent levels of mortality. And now what we found was that low affluence definitely does predict poor mortality, all the way through to high affluence predicting low mortality. So subdividing the data, so after a lot of experimentation, and a lot of that was in terms of the working out what the right index was, we were focusing on males, and it's almost the whole population, but not quite, because particularly with income, we need to have a full 12 months of income within Denmark. So we have therefore excluded people within the population who've perhaps been out of the country for a few months, or that they are an immigrant and have less than 12 months of income. We then, for year T, we would then subdivide the population. It's divided into 10 roughly equal-sized groups. It's on the basis of this affluence measure, and it's the affluence in the previous calendar year, because we want to allocate, we want to have the information at the beginning of the year to allocate them to a particular group. So individuals are allowed to change group up to age 67, but then after age 67 we found that it was better to fix the group that they were in. So once you reach age 67, which is the state retirement age, that's why we chose 67, once they get to 67 they just stay in the same group regardless of how their affluence goes up or down after that. And as I commented at the bottom, that was better in terms of analysing the results. That was better than not locking them down and allowing them to continue to transfer. So we've got ages 55 to 94. We didn't start in 1981 because there were some issues with the data in the first 4 calendar years within the database. So we started from 1985 up to 2012, so that's covering 28 years, and then we have the exposures and then the indexes. Looking down here, so the 3 indexes for exposures and the deaths and the death rates, population I, so 1 up to 10, calendar year T, and age X. So for the exposures, having subdivided, the exposures run from 4,250, which would be probably all 10 groups, but at the youngest age in age 55 in one of the calendar years. I can't remember which one, but probably the later years rather than the earlier years. So over 4,000 in the youngest age groups, and it goes down to the smallest value of 13, which would be at the highest ages, probably 94, and that would be in group 1, which is the lowest affluence group, because in the lowest affluence, that's the group where people die off most quickly. On the death side, death counts range from 151 down to 4. 151 would be at the peak mortality or peak death counts, and that would be sort of around about age 75 or sort of in that sort of range of ages. And the 4 could either be at the youngest or the oldest ages, but in this particular case it was that was at age 55. That was the lowest death count. And then, given the deaths and the exposures, we've got the crude death rates, which are simply deaths divided by the exposures. Now, the point about mentioning the death counts in particular is that, especially where you have these single-digit death counts, then the sampling variation, Poisson risk, is going to be very important within the overall analysis of this data. And you do need some modelling, some smoothing in order to filter out that noise that you get. Nevertheless, so this is a plot of the crude age-specific death rates in 2012, and even though for the 10 groups, so we've got group 10 up at the top, the black line, and then the dotted red line is group 10, the most affluent and the least affluent. You can see, yes, there is a lot of noise within these crude age-specific death rates, but nevertheless you can see that the death rates for group 10 are very much lower, particularly the younger ages compared to the group 1 up at the top. But I'll show you a graph in a couple of slides' time where I've done a bit of model-based smoothing where things look rather clearer. But that's just there to say, well, without doing anything to the data, that's the basic data set. And we've got similar plots, of course, for 1985 up to 2012. So we then now do think about doing a bit of modelling. So we're now thinking about modelling the death rates, the underlying death rates, as opposed to the crude rates themselves. This is the model that we were using to do that. So we've got, in this model, it's a form of CBD, or an extended CBD model, where there are 2 period effects or random processes, kappa 1 and kappa 2, which are specific to each of the 10 subgroups but change over time. And then kappa 1 itself, that's just on its own and represents the level of mortality typically going down. whereas kappa 2, it's times x minus x bar, the age. And so kappa 2, or changes in that, are telling you about changes in the slope of the mortality curve. So is it getting steeper or less steep over time? And then there's a non-parametric beta x, which is different for each of the subpopulations. So we've got 10 groups, 28 years and 40 ages. And I'll talk a little bit later about the actual fitting of that model, but in advance of that, here are the results of the modelling. So this is the plot that you've already seen with the crude rates. And then after you've applied the model, you get a rather smoother set of mortality curves, where it's very much more clear about what the differences are between the various subgroups of the population. And in fact, the smoothing has certainly worked out well enough, bearing in mind that there is a non-parametric beta x. So there is a very clear separation of the 10 groups and a clear ranking. So at all ages, you have a ranking of group 1 at the top down to group 10, with occasional touches, particularly you can see up at the top that groups 1 and 2 are touched from time to time, but broadly speaking, group 2 is below group 1. And overall, you can see that clear separation. And it's a similar picture for all 28 years. And it was getting to a plot that looked like that, with that clear separation at all ages. That was what took us about 3 years of effort in terms of going backwards and forwards from the national database to try out different measures of affluence, etc. But finally we got to this set of plots where it was a similar plot in every single calendar year, and then we sort of sat back and breathed a big sigh of relief. So there's the model up at the top. It does fit the all 10 groups well, without the need to put in a cohort effect or indeed additional period effects. The non-parametric term that we have here, that was necessary. So we did try a pure sort of CBD type of model without that. But in order to get a good ranking and without losing the genuine detail in the data, to get to a good ranking in the smoothed mortality rates, we didn't need to have these non-parametric effects in. And in particular, if you took these out and just had the linear terms, what you would find is that you end up getting a bit of a crossover at the very high ages, which is not actually there in the original data. It's just that the linear part is not quite enough to get a good fit across all ages. And the key point, of course, is that those rankings that we get they're certainly evident in the crude data, but we get rather crisper rankings between the different subpopulations within the crude, within the smoothed data. And in particular, more affluence across all 10 groups means that you're more healthy and you have lower mortality. Now, just sort of discussing some of the detail of that. So, in a way, this is where the sort of shocking part comes in, that you get these headline differences between the well-off and the worst-off in the population. So, for example, at the youngest ages, at age 55, the mortality rate in the low affluence group is 5 times the mortality rate in the affluent, most affluent group. And then it reduces to about 1.3 times up at the highest ages. But that convergence is sort of well known from other sorts of studies, but it's more here, what are the sort of magnitude of those numbers. And of course, you might also think, well, you thought that Denmark was a socially equal country, but in reality, the differences are arguably almost as big as, say, the UK or the United States, where there's probably rather more perceived inequality. But in terms of mortality, Denmark suffers almost as much as these other countries. So moving on, other sort of summary statistics. Here are some period life expectancies. So I'll maybe just pick out age 55. So this is the expected remaining lifetime from age 55. Again, you can see very big differences between the least affluent down at the bottom going up to the top, and that sort of difference is around about 7 years or so, and it is actually, it's maybe not quite so clear in the plot, but it is actually wider, it has widened slightly over the 28-year period of the data that we have. And then because the underlying mortality rates converge as you get older, then the gaps in life expectancies also get a bit narrower over time. So the next thing is to really sort of rewind and tell you a bit about the time series modelling and how we fitted that model. So the key point in terms of one step ahead and multi-steps ahead, we need to allow for some correlation, and that correlation, there's two types. So that there's within a subgroup you have two period effects, so we need to model some correlation between kappa 1 and kappa 2. And then we also need to think about between the subgroups. And then as you go into the longer term, then the sort of key idea is that the actual mortality rates for different groups, that they should not be allowed to diverge to any significant extent. So the sort of relative differences will in some sense remain stable, so they're not all going to converge to the same mortality rates, but if one historically has been about 50% of another group, then over time that ratio will fluctuate. Both groups will improve, but that ratio will stay around about 50% or maybe 60 or 40, but not go off to zero and not cross over it and go in the opposite direction. So we need to include some sort of mean reversion or something which prevents the subgroups from diverging. So this resulted in this particular relatively simple specification for the time series dynamics. So we've got a sort of what you can think of as being a bit of a sort of random walk component, but then there's a bit of an adjustment to that, which I'll sort of outline in a bit more detail on the next slide or two. But within this, there's a kappa 1 bar and a kappa 2 bar. So we've got 10 populations, all with their own period effects, and the kappa 1 bar is the average across all 10 groups, similarly for kappa 2 bar. So the significance of these I'll explain coming up. So within this, in terms of the modelling, so the kappa 1 and kappa 2, because of the simple structure of the model, this turns out to be simply a bivariate random walk. And then kappa 1i, so that the subpopulation period effect, the difference between that and the average across all 10, this is modelled as an AR1 time series, which is mean reverting to 0. So that's by choice. It's a form of identifiability constraint within this model. And similarly, the difference between the population of the subgroup kappa 2 and the kappa 2 bar, that's also an AR1. Now the fact that these are assumed to be mean reverting to 0, that means that the betas themselves, the non-parametric age effects, these are what capture the intrinsic differences between the different groups. So the low affluence group will have a high set of values for the betas. Group 10, high affluence, would have a set of low values. Then we have to think about the correlation. So we've got the Zs here, first of all, and it's a very simple assumption. So there's a Z1 and Z2 for each subgroup, and Z1 and Z2 are, the correlations are governed by these V terms. So there's 3 of those in terms of the covariances. And then when you look at between subgroups, there's a single parameter governing all of those, rather than a complete matrix of values for the correlations between subgroups. So that's a very strong and simple assumption in order to keep the number of parameters that need to be estimated relatively small, but then it's of course up to the modeler to then check, well, is that assumption about simple assumption about correlation, is that a sound one, or does that need some more generalization? So that rho can be thought of as being a correlation between kappa 1 in two different subgroups. So it's a very simple model. There's, oops, if I just go back. So there's also up here, there's the, in terms of the AR1 models, the AR1 models all have the same mean reversion rate. So that's another strong assumption that needs to be tested and considered. So it's a very simple model. We've got one gravity parameter rather than there potentially could be 20, provided you stick with AR1, and then we've only got this one correlation parameter rho, in addition to the 2x2 covariance matrix, the little v's. And so therefore many generalizations are possible if the data suggests that that is necessary. But of course, the more parameters you put in, the more complex things become, and the computational side of things, the Markov chain Monte Carlo, for example, becomes much more challenging. But the key conclusion from this data actually was that this very simple model did indeed seem to fit the data pretty well, but nevertheless there's scope for further work on that front. So just quickly on the Bayesian side of things, we had, as far as possible, uninformative priors, but we did need to be rather more specific in some cases. So we had an inverse Wishart distribution for the 2x2 covariance matrix. We had a beta 2,2 distribution for the correlation parameter rho, and similarly for the gravity parameter psi, and the estimation was using a mixture of Gibbs sampling and Metropolis Hastings. One or two illustrative results coming out of that analysis. So or mu1 is the drift for the period effect, or that's the average period effect for the kappa 1s across all populations, and the way to interpret this distribution here is that the average improvement rates across all ages, because that's what kappa 1 governs, the average improvement rate is around about 1.8% per annum in the middle of the distribution, but that improvement rate could range from around about 2.4% at the upper end and maybe 1.2% at the other end. So there's a sort of reasonable range of values for mu1, and that really reflects the fact that we've only got 28 years worth of data for the Danish population. And then plots for rho and psi, and of course the correlation parameter rho, so that's sort of in a sort of reasonable sort of middle of the range values. Psi is rather closer to 0, so that's telling us that the gravity parameter is not very strong, so the individual subgroups can drift away from each other to some extent. So of course this was one where we did do a bit of sensitivity testing with respect to the prior distribution, just to make sure that for the quantities that we're really interested in, such as mortality rates, that they were not or to what extent are they sensitive to that choice of prior. So thinking now about correlations, so I'm an actuary, I'm interested in the correlations between these groups, and in particular what for example are the correlations between one subgroup and the national population. So here we're plotting the group, and this QX here, this is the mortality rate rather than the death rate, versus the total, which is simply the national population. And the different plots are 1 year ahead, 5 years, and 25 years ahead. And as we go from one across to the other, so there's a scatter plot with 1,000 simulations in each. The scatter plots become more dispersed as you go to the right, and that's because there's more uncertainty in the future. They shift down and to the left, that's the improving mortality, but also the correlation increases, and the increase in correlation is the result of the gravity parameter that's in the model. Now, those correlations were for single deciles out of the 10, but in actuarial terms, of course, the typical population that you're looking at is not such a narrow subgroup of the population, and so there are other examples that you could look at, such as blue collar or white collar groups, which are maybe, in my cases, are the average over 3 subgroups rather than just single ones. And then there's a mixed plan, which is even more diversified. So for QXs, the mortality rates, this is just one example, where you can see the over time now, this is the time horizon, quite relatively high correlations, just 1 year ahead. These are the 10 deciles down at the bottom, and then you have higher correlations for the white collar and blue collar plans. So the things to think about here are why are they all at different levels, and the reason is that for the deciles, group 1 is close to the top and group 10 is at the bottom. The reason for that is quite simple, that in terms of numbers of deaths, it's the people in group 1, the low affluence. These are that's the subgroup that has the largest number of deaths. So that contributes more than 1/10 to the national population death count, at least at age 75. So that's why group 1 is at the top and group 10 is at the bottom in terms of correlations with the national population. And then with the blue and white collar, it's simply about diversification. So if you have 3 groups rather than 1, you are moving towards the whole of the national population. So correlations go up. And then there's a similar plot for cohort survivorship, but I'll not look at that for too long. I don't want to perhaps skip ahead. There's another correlation plot which is looking at the correlation between the survivor index, proportion who survive over 10 years for a particular subgroup, but then looking at the total or the national population, but looking at different ages. So you can see here that the correlations are highest where the X in the national population is close to the age that you're interested in. So here I've just chosen age 67, and it's a sort of natural or intuitive thing that the further apart the two ages are, the lower the correlation. So in terms of modelling conclusions, we've done a development of a new multi-population data set, which hopefully we'll be able to publish that data set itself relatively soon so that other people can try things out. But we do get these strong and quite reasonable group rankings across all ages in all years. And because we're looking at affluence rather than anything else, that we do have this ranking that you don't necessarily anticipate when you're looking at national populations. We've also got a new multi-population model, and then mortality rates converging at high ages. So that's really summarising the sort of main part of the talk, but if I can go on for just a few minutes more, there's some very recent research, and this is to look at education as an alternative covariate. And so in the original work, it wasn't something that we had particularly focused on. We had in our minds that we wanted to look at something related to income or wealth, but inevitably when we submitted the paper, a referee came back and said, "You've got this fantastic data set. I wouldn't do anything at all to do with income and wealth. I would do education." So of course we thought, well, we're not going to rewrite the paper completely, but of course we did have to reanalyze the data in order to satisfy the referee that we were doing good work. And it did generate some very interesting discussions, which is why the revision took so long. But but it sort of gives rise to some interesting questions for future work rather than rewriting the paper. So the key idea is that the level of educational attainment is also known to be a good predictor. So lots of studies based on US data and a couple of other papers that I've mentioned where Mackenbach and others look at a number of European countries. They look at age standardized mortality rates, and Broom and Hansen and Bodsgaard, they look at Danish data, so it's the same data set, but all they quote is life expectancies for an individual aged 30. So what we were able to do was we put our sort of CBD type modelling to one side, so we didn't do any smoothing to the data, but we tried to calculate these similar statistics using our crude data. And so we were looking at age 30 up, so we do have the data for that, even though I've looked at age 55 to 94, and looking at corresponding calendar years. And what we found was that affluence gave a markedly wider spread of standardized mortality rates than those that were in the Mackenbach paper, and also a wider spread of life expectancies than in the Danish paper. So there were good reasons for using affluence, and simply that it's a rather better discriminator in terms of the high versus low affluence compared to the high education versus low education. And a further issue with education, it's a good covariate, but you have to bear in mind that there is what you might call grade inflation. So as the years go by, more people are reaching the sort of middle level of education and also higher education, and you have to try to take account of that. But what that might end up with is, for example, that if you look at the people who have low education, so that's less than a full high school education, that these individuals potentially are becoming increasingly concentrated within the most deprived in society. So that on its own could cause the mortality rates of low educated people to go up. So you have to keep that in mind when you're analysing mortality by level of education. And here's a couple of plots to illustrate what I just said. So these are age standardized mortality rates, and it's over a 10-year group of ages, 45 up to 54. So at the top and the bottom, we've got the low affluence and the high affluence, and then we've got low education and high education that are in between those. And of course, you can see that all of them are going down just, so that the low education is the one that's perhaps flattest of all, but it's well inside the affluence groups. And on the other hand, the high education people are they're improving at pretty much the same rate as the high affluence individuals in the population. So things are going right for those individuals, but not so well for the low education people in relative terms. And then this is a different way of illustrating our results, and in fact this is slicing and dicing things a bit more now. So in this plot, first of all, what we did was to don't just look at affluence or education, but actually to take the 10 affluence groups, but then subdivide by...
Sorry, okay, we'll just wrap that up.
Right, okay, so there's very strong improvements amongst the higher, but not the most affluent, and but also the higher education is a good thing in terms of improvements, whereas the poorer, but not the poorest, and also low educated have actually got worse, their mortality. And this is over a period of 22 years that that particular group, their mortality has worsened, whereas this group, their mortality rates are now 1/3 of what they were 22 years ago, which is quite a shocking end. On that bombshell, I will finish. Thank you.
Thank you very much. We'll move up now to 582041 for some coffee and refreshments. I think we're going to have to vacate from the...
I can bring the plots with me for anyone that wants to talk about socio-economics.
Thanks very much, and thanks to Angie.
Right. Sorry. No, it's fine.
It's really interesting. Let me see if I can stop this.